Good morning everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this class, we will talk about elastic critical moment MCR for concentrated load. In the previous class, we have learned many things. In practice, beams are subjected to a variety of loading conditions. As you can see from the loading diagram on the left hand side, you can see that MA and NB are acting in such a fashion that it leads to a single curvature, but MA and MB can also act such that it produces a double curvature. The corresponding bending moment diagrams are shown on the right hand side, as you can see here. And M critical is obtained using the energy method I equal to U plus V, where U is the strain energy of the beam and it has got four components, V, U, gamma as well as the warping component. Usually the first term V is neglected simply because the V is very low compared to U and gamma. That is, the vertical displacement is very low compared to lateral displacement U and the twist gamma. The potential energy for a uniform moment is given as minus mx into 0 to L du by dz into d gamma by dz into dz, where U equal to A sin pi z by L and gamma equal to B sin pi z by L. For non-uniform moment on either sides of the support, we have the potential energy V as mx into 0 to L gamma into d square U by dz square into dz, where U equal to A1 into sin pi z by L plus A2 into sin 2 pi z by L. Here, two terms are taken into consideration because there is a possibility of reverse curvature and hence more terms are taken into consideration. Gamma equal to B into sin pi z by L. Now, we have solved for the uniform bending moment diagram, where the elastic critical moment M critical is given as N0 critical equal to pi by L the whole square into EIY into root of IW by IY plus GJL square divided by pi square EIY. We have also solved for non-uniform moments acting on either sides of the support. Here, M critical divided by M0 critical is equal to CB, where CB is defined as the lateral torsional buckling modification factor as per AISC. The CB is derived as 0.282 minus 0.436 psi plus 0.282 psi square, the whole power minus half. This is derived based on approximations, and CB equal to 1.75 plus 1.05 psi plus 0.3 psi square, which should be less than or equal to 2.3. This is adopted by AISC in 1961 till 1986. Now, what happens when we have a concentrated load at midspan? So, we have the corresponding bending moment diagram as shown here. And what is the potential energy for such loading case? So, this is what we need to find out today. So, we have the concentrated load that is acting at the shear center, and assume that the ends of the members are laterally restrained, which is U equal to 0, free to bend about minor axis, which is U double dash is equal to 0, restrained against to twist, which is gamma equal to 0, and free to warp, which is gamma double dash equal to 0. Now, let us establish the total potential energy pi of the beam. So, pi equal to U plus V, and we have a long equation that is shown in the screen here. Here, the first term, as I said previously, it has to be omitted because V is very much less than U and gamma. So, it boils down to the equation that is shown on the figure. The first three terms relate to strain energy U, and the fourth one is related to potential energy V. Let us derive expression for the potential energy V due to concentrated load P applied at the shear center of the I section. So, lateral buckling of I beam with concentrated load, we can see that the P is applied at the shear center. Upon application of a concentrated load at the shear center along the midspan of the beam, it undergoes both vertical and lateral displacements, as you can see on the figure on the left hand side. From stage 1 to stage 2, the beam deflects vertically by V. Later, it deflects laterally with a displacement of U and twist with an angle gamma simultaneously from stage 2 to stage 3. This phenomenon is referred to as lateral torsional buckling. Henceforth, the beam displaces vertically with a magnitude of W from stage 2 to stage 3 due to lateral torsional buckling. Nevertheless, the lateral displacement U is much larger than the vertical displacement W. However, of the two displacements U and W that make up the buckling displacement, only W contributes to the potential energy V of the applied load P. Therefore, the potential energy of P is given by V equal to minus P into W. Let's determine W. For small deformations, the increment in vertical displacement dW that corresponds to du can be considered as follows. So, from looking at the figure on the left hand side, And by using trigonometry, we have tan gamma equal to dw by du. For small values of gamma, tan gamma equal to gamma, which means that dw equal to gamma into du, which becomes equation 1. du is the deflection due to component of external moment about y dash axis due to p. So determining du. Using moment area method to find the deflection du. So the deflected shape under lateral bending due to my dash is given below. So here we can see that the displacement is du for a small length dz. So the deflection du as per the moment area method is the moment of area between dz of my dash by eiy diagram about O. O is the origin. So when we do so, we have du equal to my dash divided by eiy into dz into the lever arm, which is z plus dz by 2. When we expand this equation, the second term can be neglected due to higher order terms. So we have du equal to my dash divided by eiy into z into dz. Now that can be substituted in equation 1. When we do so, we have dw equal to gamma into my dash divided by eiy into z into dz. Integrating on both sides, we have w equal to 0 to L by 2 into, we have w equal to 0 to L by 2, dw is equal to 0 to L by 2 gamma into my dash divided by eiy into z into dz. Now let us find the component of moment of external moment about y dash axis due to load P. Assuming that the beam is subjected to equal end moments mx and resolving the moment about y dash axis, when we look at it through xy plane, which is the cross-section plane, we have this one which is deflected. The original axis is given in the blue color, which is x and y. The deflected axis is given in x dash y dash. And the angle of twist is given as gamma. When we resolve these components, we get the following values here, which is mx is in the direction given here, which is the externally applied load. Now resolving these components, we have mx dash equal to cos gamma into mx. Assuming that gamma is very small, we have cos gamma equal to 1. So this mx dash becomes mx. Similarly, my dash equal to sin gamma into mx, and for small values of gamma, this becomes gamma into mx. Now we can substitute the value of my dash in the above equation, which means that my dash equal to gamma into mx. However, the beam is subjected to a concentrated load P at midspan, and hence it is important that we transform this mx as a function of P. So when we do so, we take the cut section here. So when we take summation of moments about A, we have mx minus P by 2 into z equal to 0, which indicates mx equal to P by 2 into z. So we can substitute the value above. So we have my dash equal to gamma into Pz by 2. And so w equal to 0 to L by 2 gamma into my dash divided by eiy into z into dz. Now substituting the value of my dash in w, we have w equal to 0 to L by 2 into gamma into Pz by 2 into gamma divided by eiy into z into dz. Now we also know that the potential energy of the load P equal to V into minus P into W. So we have V equal to minus P into 0 to L by 2 gamma into Pz by 2 into gamma divided by eiy into z into dz. So this gives rise to the equation V equal to minus 0 to L by 2 P square z square gamma square divided by 2 eiy into dz. Now we can substitute the value of V into pi. So we have a big long equation here. And we also know that from the component of external moment mx about y dash axis, we have my dash equal to gamma into mx. Now the internal resisting moment, as you can see here, when we look at the plane x and z, the curvature is minus d square u by dz square. So my dash can be written as eiy into minus d square u by dz square, which is the internal resisting moment. So equating the internal resisting moment with the external load for achieving equilibrium, we have eiy into minus d square u by dz square equal to gamma into mx. So d square u by dz square equal to minus mx into gamma divided by eiy. We also know that mx equal to p by 2 into z from the previous slide. So we have d square u by dz square equal to minus pz by 2 into gamma divided by eiy. Now we can substitute this value in the first term that is given here in the pi equation. So when we substitute that, we have pi equal to 0 to L into half into EIY into minus Pz by 2 into gamma divided by EIY the whole square into dz. So we are basically substituting instead of d square u by dz square minus Pz by 2 into gamma divided by EIY. The remaining terms remain the same, and hence when we simplify this further, we get the equation. Hence when we simplify this further, we get the equation as shown here. And this again can be simplified by making sure that the 0 to L integral can be written as 2 into 0 to L by 2. This is done to facilitate the addition of the another term, which is the fourth term that is given in the pi equation, which is the potential energy term. So when we do so, we can simplify this further and we can add the first term and the fourth term. When we do so, we have pi equal to 0 to L into half into Gj into d gamma by dz the whole square into dz plus 0 to L half into EIW into d square gamma by dz square the whole square into dz minus 0 to L by 2 p square z square gamma square divided by 4 EIY into dz. So now let us use the approximation gamma equal to A sin pi z by L. So let us check if these approximations satisfy the boundary conditions. Here we have only one constant A. So the two boundary conditions are sufficient. So gamma dash is given as A into pi by L into cos pi z by L. Gamma double dash is given as minus A into pi by L the whole square into sin pi z by L. So we can check the boundary conditions C and D. So for C, gamma equal to A sin pi z by L. So gamma at z equal to 0 equal to A sin pi 0 into L, which is equal to 0. So gamma at z equal to L equal to A sin pi L by L, which is also equal to 0. So gamma double dash again is a function of sine. So we have gamma double dash equal to minus A into pi by L the whole square into sin pi z by L. So gamma double dash at z equal to 0 is 0. And similarly, gamma double dash at z equal to L equal to 0. Now the boundary conditions are satisfied. So let us substitute the approximation for gamma and its derivatives to obtain the total potential energy equation of the beam pi. So when we do so, we get this equation above. Now we can simplify these terms after substituting this gamma term. And when we use the integrals on the right hand side, which is 0 to L sin square pi z by L into dz equal to L by 2. And similarly 0 to L cos square pi z by L into dz equal to L by 2. And then we have 0 to L by 2 z square into sin square pi z by L into dz is equal to L cube by 8 pi square into pi square by 6 plus 1. So when we substitute these values, we get a much simplified pi value. So using the principle of total, so now using the principle of stationary potential, total potential energy, we can find out for equilibrium the total potential energy of the system pi should be equal to 0, which is del pi equal to 0. So the critical moment is reached when the neutral equilibrium is possible. The requirement of neutral equilibrium is such that the partial derivative of pi with respect to A should vanish. Now when we differentiate this pi value with respect to A, we have an equation which has to be equal to 0. Now we can take A common outside and we get this equation here. For non-trivial solution, we should know that A not equal to 0. This means that the values inside the bracket should be equal to 0, which is pi square Gj by 2L plus pi power 4 EIW by 2L cube minus P critical squared divided by 2 EIY into L cube divided by 8 pi square into pi square by 6 plus 1 bracket close should be equal to 0. So we can simplify this further by multiplying with 2 EIY into L by pi square on both sides. We can simplify this further again by multiplying with pi square by L square on both sides. And further simplification gives rise to this equation as you can see here. And we can take the square on both sides. We can simplify this further and we can represent in the form of P critical into L by 4 the whole square into pi square plus 6 divided by 3 pi square on the right hand side. This P critical into L by 4 is nothing but MCR for a point load. So we have pi square EIY by L square into Gj plus pi square EIW into L square is equal to MCR square into pi square 6, which is equal to MCR square into pi square plus 6 divided by 3 pi square. So now we can apply square root on both sides. This simplifies this further. Now we can multiply and divide with root of pi square plus 6 divided by 3 pi square on both sides. So we get a clean equation on the right hand side, which is MCR. And we know that the elastic critical moment for equal end moments M0 is given as root of pi square into EIY divided by L square into GJ plus pi square EIW by L square. So now we can simplify this further and represent in terms of M0 critical, which means that 1 by root of pi square by 6, which means that 1 by root of pi square plus 6 divided by 3 pi square into M0 critical is equal to MCR. So MCR divided by M0 critical is equal to 1 by root of pi square plus 6 divided by 3 pi square, whose value is nothing but C sub B, which is the lateral torsional buckling modification factor. So when we compare this one, we have C sub B equal to 1.365 or approximately 1.37. Now when we look at the lateral torsional buckling modification factor, which is M critical by M0 critical equal to CB for various loading conditions, we have for uniform moment 1.0. For non-uniform moments on either ends of the support, we have CB equal to 1.75 plus 1.05 into psi plus 0.3 into psi square, which should be less than or equal to 2.3. Here psi is defined as M minimum by M maximum. And for a point load, it is given as 1.37. And for point load, we have derived it as 1.37. Now this is based on the assumption that the load is acting at the shear center, which is a normal condition. For destabilizing condition, the load acts on the top flange, and in rare situations, the load could also act at the bottom flange, which is also known as stabilizing conditions or simply normal condition. Now the first one, which is the load acting through the shear center, has been solved. Now for this condition, which is destabilizing condition, where the load is acting at the top flange as well as the load acting at the bottom flange, we need to understand how to solve this problem. So for concentrated load acting at the midspan, we have the bending moment diagram, and for uniformly distributed load acting at the for uniformly distributed load, we have the following bending moment diagram. And the CB values for load at the bottom flange is given as CB equal to A into B. For load at the shear center, CB is given as A, and for load acting at the top flange, CB is given as A by B. And this equation has been taken from Nethercott and Rocky. The title of the paper is A Unified Approach to the Elastic Lateral Buckling of Beams by Nethercott and Rocky, published in 1971 in AISC Engineering Journal. Similar derivations are also given in a slightly modified form in the equation in the book Structural Stability Theory and Implementation by W.F. Chen and Eric M. Louis, Elsevier Science Publishing in 1987. So here A equal to 1.35 and B equal to 1 minus 1.779 divided by R square plus 2.039 divided by R. This is only for a concentrated load at midspan, and R square is defined as L square GJ divided by EIW. For uniformly distributed load, A equal to 1.12 and B is given as 1 minus 1.522 divided by R square plus 1.681 divided by R. What happens if the bending moment diagram is not linear and there is a non-uniform bending moment diagram, as you can see here? How does CB vary? So the lateral torsional buckling modification factor MCR by M0 critical is equal to CB, which is given as, here CB is given as 12.5 M max divided by 2.5 M max plus 3 MA plus 4 MB plus 3 MC. This is based on the provision given in AISC 360, section F1, page 16.146, as you can see from the right hand side. Here, it should be noted that the beam is assumed to be torsionally restrained at the supports, which means that it is restrained against twist, which is gamma of the cross section, and rotation along the longitudinal axis alone, which means that warping is allowed in this cross section, which means that the warping is allowed in the support conditions. Now let us consider the lateral torsional buckling modification factor CB for various loading cases. For linear moment diagrams, it is 1.75 plus 1.05 psi plus 0.3 psi square. And for non-linear moment diagrams, it is given as 12.5 M max divided by 2.5 M max plus 3 MA plus 4 MB plus 3 MC. So let us look at how these two equations vary for equal end moments. For equal end moments, we can see that the value of C sub B, when we substitute psi equal to minus 1, we have C sub B equal to 1.0. And when we consider the bigger equation, which is for nonlinear moment diagrams, we can see that the C sub B is again equal to 1.0, as you can see from the right hand side, because the M0 does not vary along the length of the beam. For unequal end moments, which is linearly varying moment, which is given here, the bending moment diagram, we have C sub B equal to 1.75 plus 1.05 psi plus 0.3 psi square. So when we substitute psi equal to plus 1, we have 3.1. Again, it should be less than or equal to 2.3. So we can take CB equal to 2.3. When we consider the CB factor based on the nonlinear moment diagrams, we substitute the value at each location, which is MA represents the 1/4 and MB represents the center and MC represents the 3/4. We get CB equal to 5.0, which should be less than 2.3. So for concentrated load at midspan, when we try to obtain CB using the nonlinear moment diagrams equation, we get CB equal to 1.31. For uniformly distributed load, we have CB equal to 1.12. We have not derived this value CB in our class so far, but please take into mind when we derive that, we get CB equal to 1.12. And when we check with the nonlinear moment diagram equation, we have 1.136. It is obvious that 1.12 is over-conservative for nonlinear moment diagrams because the value of 1.12, which is a multiplication factor, is less than 1.136. Similarly, the C sub B obtained for the other case, which is loaded at the midspan, we have C sub B equal to 1.35, and the 1.35 is unconservative for linear moment diagrams compared to C sub B, which is 1.31 obtained from the equations that are currently present in the code. It is unconservative because 1.35 is greater than 1.31 and 1.35 is a multiplication factor to enhance the resistance of the MCR value. So having a value of 1.35 which is greater than 1.31 is unconservative for linear moment diagrams. With this class, we have completed the portion for beams under various loading conditions. We will talk about various support conditions in the next class. Thank you very much.